Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with our previous topic. Remember, in the last lecture, we introduced the course Modern Physics first. Then I told you there are four units in your syllabus: Unit first, Unit second, Unit 3, and Unit 4. And we started with Unit first, where we discussed the topic black body radiation. Now, in this lecture, I write here continued. This topic we are continuing in this lecture as well. So, in the last lecture, we talked about thermal radiation. We said that all bodies radiate electromagnetic energy, and that radiation is called thermal radiation. At any temperature, electromagnetic waves are being emitted by bodies. Now, then we defined the ideal body which we use to study this thermal radiation phenomenon. We defined black body as the body that absorbs all radiation incident upon it, regardless of frequency. Then we said that how we approximate such a body in lab. We do the cavity approximation. Then we talked about the spectrum of such a black body. These were the curves. When we plot spectral energy density, U nu, D nu, where U nu, D nu is the energy per unit volume radiated by the black body in the frequency interval from nu to nu plus D nu. When we plot it frequency versus frequency, we get these curves. Here, the first curve, we have temperature 1200 Kelvin, and for the second green curve, the temperature of the black body is 1800 Kelvin. Then we notice certain things from this graph. We notice it that as frequency increases, this spectral energy density first increases, then decreases. And at higher temperature, the curve has the same shape, but the area under curve is larger and the peak is shifted to higher frequency end. In this green curve, you can see the peak is at a higher frequency, right? Then we said to explain this phenomenon, this black body spectrum, there were two people in the at the end of the 19th century, Lord Rayleigh and James Jeans. What they did to explain this black body spectrum, they used the idea of standing waves. They said in the cavity with perfect reflectors, the radiation can be considered as the collection of three-dimensional standing waves. Then they calculated the number of independent standing waves in the frequency interval between nu and nu plus d nu per unit volume in the cavity, which turned out to be 8 pi nu square d nu over c cube, right? Then the second part of the problem was to find the average energy per standing wave. For that, they used the idea of theorem of equipartition of energy, where it is stated that at thermal equilibrium there is associated an average energy of half kT per degree of freedom per molecule. Then we said this theorem is equally valid for collection of radiation, which is at thermal equilibrium, or collection of radiation and matter as well. So they used this theorem and justified that the average energy per standing wave is kT because the radiation is in equilibrium with the oscillators in the cavity walls, and oscillators are one-dimensional harmonic oscillators. One-dimensional harmonic oscillator has 2 degrees of freedom, so per degree of freedom it will have half kT. The total average energy per oscillator is twice half kT, which is kT. So since these oscillators are in thermal equilibrium with standing waves, Average energy per standing wave is kT. K is Boltzmann constant. Then to get the spectral energy density, they multiplied this average energy times this function G nu d nu, number of independent standing waves in this particular frequency interval per unit volume. They got this result which we called Rayleigh-Jean's law. Then we said, now the question is whether this, if we plot the spectral energy density from Rayleigh-Jean's law with frequency, whether the curve matches the experimental curve or not. So let us plot that today. Let me use this red color. So if we plot, we have already plotted this spectral energy density. Now I will give the comparison of experimental curve with the Rayleigh-Jean's curve. So when we plot this spectral energy density u of nu d nu versus frequency nu, this is our experimental curve. We get this type of curve. Let me change the color. I call it observed. This is the observed one, observed spectrum. But the Rayleigh-Jean's law goes like this. This is what we get if we use Rayleigh-Jean's law. So you can see Rayleigh-Jean's law fails for high frequencies. We write fails at large frequency and is okay at low frequency. At low frequency, the curve for Rayleigh-Jean's law matches or coincides with the observed curve. So let us move to this equation. You can see this spectral energy density from Rayleigh-Jean's law increases with nu square. So if u of nu d nu, you can see if nu approaches infinity, let me clear this if I have to write it this way. If nu approaches infinity, from Rayleigh-Jean's law, you can see u of nu d nu, that is spectral energy density, will approach to infinity as well because it is proportional to nu square, right? That is indicated in this figure as well. It is going up the curve for Rayleigh-Jean's law. And in reality, we're seeing that in reality, we see u of nu d nu approaches 0 as nu approaches infinity. As you can see in the experimental curve, as nu approaches infinity, this curve comes down, the spectral energy density approaches 0. So there is a big failure at higher frequencies in case of Rayleigh-Jean's law. It says it should go to infinity, but in reality, the spectral energy density approaches 0. Now, since this discrepancy occurs at high frequencies, and high frequency zone is the ultraviolet zone. Ultraviolet zone. So this discrepancy at high frequencies, which occurs at the ultraviolet range of the frequencies, it is called ultraviolet catastrophe. Catastrophe, right? And if you talk of the radiation rate, that means the energy radiated by the black body per unit time, that radiation rate is proportional to this spectral energy density. So, what holds true for the spectral energy density, same will hold true for radiation rate. That means, according to Rayleigh-Jean's law, radiation rate is okay at low frequencies, but at higher frequencies, according to Rayleigh-Jean's law, it should go to infinity, but in reality, it must approach to zero. And this failure, as I told you, is called ultraviolet catastrophe. Now, if you that means there is something wrong with Rayleigh-Jean's law. Now, what is wrong with Rayleigh-Jean's law? That wrong was found by Planck, Max Planck. So he gave his law, which we will discuss now. That's called Planck's Planck's radiation formula. So where was the error? Error was in the classical idea. What classical idea? See, the expression for G into d nu is okay. Even now, there is no issue with this expression. The number of independent standing waves in the frequency interval from nu to nu plus d nu per unit volume, this expression for that is okay. There is no issue with it. But the issue was with this average energy per standing wave. Now, in arriving at this average energy per standing wave equal to kT, the Rayleigh and Jeans they use a theorem of equipartition of energy, which is fundamentally a classical result. And in classical physics, there is no restriction in the energy possessed by the molecules or radiation. The energy can have any value. Energy can have continuous values. That was the error. That was modified by Planck. Now, see what Planck did. I will first write that formula, Planck's radiation formula, then we will continue. Now, it was in the year 1900 when German physicist Max Planck used it at that time, which is called lucky guesswork, to develop a formula for the spectral energy density of black body radiation. So his formula is like this: U nu d nu is equal to 8 pi h over c cube nu cube d nu over e raised power h nu by kt minus 1. Let me name it equation 4. This is the Planck's radiation formula. U nu d nu is 8 by h over c cube nu cube d nu over e raised power h nu by kt minus 1. K you know is Boltzmann constant, nu is frequency, c is speed of light in vacuum, h is Planck's constant. H is Planck's constant. You know its value is 6.0 6 into 10 raised power minus 34 joules second. If you see in the Planck Rayleigh-Jeans formula, there is no such constant in the expression. There is no H. There is only K, C, and nu. And there is temperature, of course. And here, in case of Planck's radiation formula, there is another constant called. So in this expression, there is Planck's constant. There is nu q, and the dependence of temperature is in the denominator in the exponential form. One thing we know from sure from this graph, that Planck's radiation law must become Rayleigh-Jeans law. That means Planck's radiation law must reduce to Rayleigh-Jeans law at low frequency, right? Because at low frequencies there is no issue with the Rayleigh-Jeans law. And at high frequencies we know u nu du must approach to zero as observed, right? Now we will see whether these two things are fulfilled by Planck's radiation law or not. See, at high frequencies, h nu h nu is larger than, very larger than, much greater than kT, and e raised power h nu by kT approaches infinity. Understand this point? At high frequencies, h nu is much greater than kT, and therefore e raised power h nu by kT, because h nu is larger than kT. So e raised power h nu by kT will approach to infinity. And when this approaches to, let me take another color. When this approaches to infinity, what will happen to u nu d nu? That will approach to zero. Therefore, u nu d nu will approach to zero as observed. So this is the first good thing about Planck's radiation law. According to Planck's radiation law, at high frequencies, u nu d nu, that is spectral energy density, and hence radiation rate, which is proportional to it, approaches to zero as observed, as you can see in this experimental curve. Now let us talk what will happen at low frequencies. Because at low frequencies, this must reduce to Rayleigh-Jeans law. So let us check that. At low frequencies, h nu is much less than kT, and h nu by kT is much less than 1. When h nu is much less than kT, h nu by kT, denominator is larger than numerator, is much less than 1. So this exponential can be approximated. See how. So let me use another page. We know e raised for x can be written as 1 plus x squared by 2 factorial plus x cubed by 3 factorial. This is x cubed plus so on. 2 factorial means the product of first two natural numbers, 3 factorial means the product of first three natural numbers, and so on. Now, if x is small, then we can approximate this expansion. You can write e raised to x as 1 plus x. You can drop out these terms. because when x is small compared to 1, then what happens? The terms are smaller than previous term. That means every term in this expansion is much smaller than its preceding term. So you can drop out these terms without introducing much error, and you can approximate it just 1 plus x. Now, same will hold true for this exponential c, which is e raised power h nu by kt. Now, using this approximation, I can do it this way: 1 by e raised power h nu by kt minus 1. I can approximate it. I can write it 1 by e raised power h nu by kt is my e raised power x. Instead of x, I have e raised power h nu. Instead of x, I have h nu by kt. H nu by kt is much, much less than 1. As we discussed it, when h nu is much, much less than 1, h nu by kt is much, much less than 1. So this power is much, much less than 1. So you can write e raised power h nu by kt as 1 plus h nu by kt. We use this approximation. And this minus 1 is there. This minus 1 plus 1 will become 0. So it will simply become kt will go up. It will become kt by h nu. kt by h nu. Now, therefore, at low frequencies, Planck's radiation law, Planck's radiation law becomes u nu d nu. Let me go to this formula. 8 pi h by c cube, 8 pi h by c cube, nu cube. Then there is approximation. 8 pi h by c cube nu cube, d nu, d nu, and this 1 by e raised by h nu by kt, we have proved it. It becomes 1 by e raised by h nu by kt minus 1 becomes just kt by h nu. So I write it kt by h nu. 8 by h by c cube, nu cube, kt by h nu, d nu. kt by h nu is for this whole thing. 1 by e raised by h nu by kt minus 1. So when you simplify this, it becomes, let me use next page. When you simplify this, it becomes u nu d nu is 8 pi kt by c cube. Of course, it's an approximation. 8 pi kt by c cube nu square d nu. 8 pi kt by c cube nu square d nu, which is Rayleigh Jean's law. You can check it. We have discussed it already. 8 pi kt by c cube nu square d nu. 8 pi kt by c cube nu square d nu. Right? Now, it is now established that the Planck's radiation formula at high frequencies is correct, and at low frequencies It reduces the Rayleigh-Jeans formula. So there is no issue of ultraviolet catastrophe as was in case of Rayleigh-Jeans law. As I told you, the error was in the average energy per standing wave. Now, what was the central thing which Planck did? According to Planck, we write it, according to Planck, the oscillators in the cavity walls could not have a continuous distribution of possible energies, could not have the continuous distribution of possible energies E epsilon, but must have only, but must have only the specific energies. That is, En is nh nu, h is Planck's constant, and n is 0, 1, 2, 3, and so on. Let me name it equation 5. So, this was the main correction done by Max Planck. It was not a classical idea, it was against classical physics. In classical physics, oscillators can have continuous energy, can have any energy, but he used his guesswork and restricted the oscillator energies by this condition En is equal to nh nu. So now oscillators can have either h nu or 2h nu or 3h nu or 4h nu. In between values are not possible. Now that led to the change in the average energy per standing wave. So using this condition, when we calculate the average energy per standing wave, average energy per standing wave, per standing wave. It is not kT, but it is h nu by e raised for h nu by kT minus 1. You can check it to want its calculation. Let me name 6. I can name it equation 6. So average energy per oscillator in the cavity wall, and so far average energy per standing wave turned out to be not kT as for a continuous distribution of oscillator energy, but instead h nu by e raised power h nu by kT minus 1. You can see Planck's radiation law is simply you have to, when you find u nu d nu, according to the Planck's radiation, Planck's method, Planck's theory of black body radiation, you have to multiply average energy per standing wave with the same G nu d nu, that is number of independent standing waves per unit volume in the cavity in the frequency interval from nu to nu plus d nu. You can check it. You have to put here epsilon naught from equation 6, epsilon bar from equation 6, that is average energy per standing wave, and g nu d nu from the previous equation which we used in case of Rayleigh-Jean's law was that equation, this one, equation 1. So if you take G nu d nu from equation 1 and average energy, which is not classical now, according to Planck, from equation 6, you will get the Planck's radiation formula equation 4. So I hope you got the idea where was the error and what was the modification done by the Planck in the formula of Rayleigh-Jean's law. Now I stop here. Before stopping, I would just summarize the lecture. So at the start, we said Rayleigh-Jean's law fails at high frequencies which belong to or pertain to ultraviolet region. So this failure is called ultraviolet catastrophe. At low frequency, there is no issue. Then there is some error. Where is the error? Error is in the classical physics according to Planck. So he gave another formula which at high frequencies matches the experimental observation. That means there is no ultraviolet catastrophe in case of Planck's radiation law, and at low frequencies it reduces to Rayleigh-Jean's law as we discussed it. So there was no usage of theorem of equipartition of energy, which itself is a classical physics idea. Instead, this restriction changed the scene. This restriction on the oscillator energies changed the situation. It changed the average energy per standing wave, and the Planck's radiation law was obtained. So I hope it is clear to you. You can make notes out of it. So I stop here. Don't forget to like, share, and subscribe my channel. Thank you. God bless you. Assalamu alaikum.